Good afternoon. It is Thursday, November 12th. Okay, that's good. And we are beginning the last third of the class, right? So we started with all of the definitions and variables and hypotheses and theories. And then in the middle third, we filled your toolbox with how do you do surveys, how do you do observations, how do you design experiments. And this third, we're going to be focusing on results, interpretations, and so interpreting the data and the results and drawing conclusions. So we're going to be talking about descriptive statistics, and we're going to be talking about inferential statistics. We're not going to be doing much calculating. That's for your statistics class. In this class, what we're really focused on is what are valid conclusions, what conclusions can you draw, and how do you know what conclusion you're drawing, and how do you phrase your interpretation or your conclusion. Before I get started, are there any administrative questions? No, we good? All right, and worksheet 7's open. Worksheet 7 is due a week from Monday. It's up there. I think it's the 23rd. Yes, the Monday before Thanksgiving week, right? So Thanksgiving week. And then, so we've only got 2 worksheets left: worksheet 7 and worksheet 8. We are barreling towards the end of the quarter. Yes. Were there different versions of the test? Yes? What if you forgot to bubble in the version? Luckily, you also turned in your questions, so we knew what version you had, and somebody had to hand grade it for you, but they did it with a smile on their face, and it should all be updated. Your multiple choice, is your multiple choice grade in? Okay. So your multiple choice grades should be done. I know the TAs are working furiously on the written portion. The goal is to have that back to you a week after the exam. Okay? And worksheet 6 is going to take us a while because we're going to grade the exam first. Yeah? Is it somehow not calculated into the grade? I can check the settings in the grade book. Okay, I'll check the settings on the grade book and make sure it's adding into your grade. All right. So, should we start with the post-test? The pre-test? Right, so this is where we're going. This is not material you have had yet. This is where we're going. Are you ready? Really? All right, I'm seeing a bunch of you there. You haven't had this yet. It looks like you're pretty evenly choosing all 4 of those answers. So go ahead and just put in your best guess, and we will move on. And All right, Go ahead and put in your best guess. All right, put in your best guess. It's going to be okay. We're going to learn this stuff. All right. I'm going to move on to the last one. Okay, let's go learn this stuff. Okay. Right. To start with, actually, I would like to gather some data that we're then going to analyze over the rest of the quarter. So I'm going to recruit 300 of my favorite undergraduates as my participants in a study. It's a study on decision making. It's pretty serious decision making. There will be cartoon lives in your hands. And so if if for any reason that you would be too upset to make decisions about cartoon lives, you don't need to play. You can close your eyes. But I'm going to randomly assign you into two groups, and I'm going to give each group slightly different information, and then ask you to make the same decision. Did what I just describe, was that an experiment? Yeah? And so I'm going to randomly assign you to two groups, so I'll start with two equal groups. I'm going to give different treatment. In this case, it's going to be a slightly different decision, slightly different information. And then I'm going to ask you all to make the same decision at the end. So I'm going to measure that outcome variable. So absolutely, that's an experiment, and we will be able to determine causation, because the only systematic difference between the two groups will be the information that you are given. Other than that, we would expect you to be the same. So it's about decision making and making decisions about, sort of moral decisions of letting cartoons die. I want to ask another predictor variable, and I'm thinking about if I was to ask you, because I'm just kind of thinking what else might predict what sort of decision you make. And I was thinking that, can I ask a question like, thinking to your childhood of how you were you raised to be good because there was like some higher power that was watching you and you would get punished if you weren't good? or were you raised to be good because it's right to be good, and it feels, internally that makes you feel good, and that you should do, you should be good for yourself. If I put that like on a 1 to 9 continuum, could you answer that question? Does that sound like it might be potentially be related to, with the sorts of decisions you might make? Yeah, so it's whether your morality was whether you were raised with an internal morality or more of an external morality, or was it really balanced? All right, so let's gather that data. Let's gather some data. To begin with, I'm going to have all of you, hang on a second. I'm going to put this into a separate session so I can find it again easily. So I'm going to start. You're all going to see the same information to begin with, and then I'm going to randomly assign you based on your birthday, whether you were born on an even day or an odd day. Okay, let's start. So, all right. So this is the initial information that you've got. A trolley is hurtling down a track, out of control. There are 5 innocent bystanders tied to the track, in the path of the trolley. You can save them. Okay? If your birthday is on an even day of the month, I would like you to keep your eyes open. So if you were born on the 2nd or the 16th, if your birthday is on an even day of the month. If your birthday is on an odd day of the month, I'm going to ask you to close your eyes. I will show you all the same information at the end. I'll show you the 2 conditions. But for right now, for this demonstration, go ahead and don't peek. Okay? So, even day of the month, keep your eyes open. Odd day of the month, close them. Even day people, here is your information. Go ahead and read that to yourself. Okay? Do you understand the information you've been given? Great, so switch. Everyone who had their eyes open, go ahead and close them. Everyone who had their eyes closed, go ahead and open them. And I'm going to give the other group the information. Here is your information. Do you see the information you've been given? Do you understand your decision? Okay, let's gather that data then. First off, with your clickers, please tell me which group you were in. Were you in the first group or the second group? Okay, and I'm seeing most of you there. So let's gather that, the outcome variable. All right. And I'm seeing most of you there. And so then this is the growing up, were you taught to be good? And go ahead and use a 1 to 10 scale. Oh, hang on. I'm sorry. Stop. It needs to be a numeric response, because I want you to do 1 to 10. So to get to numeric response, if you've got the iClicker 2, I think you push the blue button and then you like go over and up and oldie tiny texting and okay, and so and then you have to send when you've entered the number. So you could enter a number between 1 and 10 that tells us whether you were taught to be good, okay, and I'm seeing a bunch of you there, yeah? So 5 would be pretty equal balance, yes. Yes, you can choose any number along the scale there. All right, and I'm seeing a bunch of you there. And is that working on the reef polling as well? A bit easier? All right. I'm going to go ahead and move on. All right. So we've gathered some data, and we'll go ahead and pull that out and take a look at it. I probably won't do that in front of you today. I'll probably pull it out and bring it back to you on Tuesday. But we will be using that data. Well, what will we be able to do with that data? What question can we answer? Oh, you want to see what everyone saw? All right. So let's have a look at what everyone saw. So the first group, this is what the option you were given, right? That you could save those 5 innocent bystanders if you blocked the trolley by pushing this poor guy over the edge, and he would be big enough to block the trolley, and you'd save the 5. And the other group, you saw if you flip this switch. And so, you know, there's still one guy that's going to die. What's the difference between those two? What would you call the predictor variable there? You got to actually touch one. You know, it's how close you are to them, isn't it? It's like we could maybe call it proximity. That you're actually like standing there next to someone, you've got to push them over, or you're kind of, removed and you're just flipping a lever. And so there'd be a very close proximity or a very distant proximity. Because the 5 to 1, that's the same, right? That's not a variable. If you do nothing, you sort of let 5 people die. But if you do something, you're really killing one person, but saving 5 others. But those were the same in the 2 conditions. The big difference was that proximity. So what would the question be that we'd be able to ask of that data? So were people more willing to push the guy or to pull the lever? Or were those 2 groups the same on that willingness to do that? That's a great way of saying it. That we split you into 2 groups. We're going to look at your average, whether you said definitely or definitely not in those 2 groups, and we'll compare those and see if they are the same or if they are different. What do you predict? You think they'll be different? Which group will be more likely to save 5? The lever. Yeah, I think so too. The distant proximity we predict that would make that an easier decision to say, yes, I would do that. We would also be able to look at that continuous variable that we measured of was your morality, were you raised with a very external morality or were you raised with a very internal morality, and see if that makes a difference in those decisions. So, that's where we're going over the next few weeks, the last few weeks of the quarter. So, in this section we're going to be talking about descriptive statistics. We're going to back up and look at some preliminaries and review what we know about variables. And then we're going to talk about what we do with categorical outcome data sets and what we do with continuous outcome data sets. This is review. Variables must vary. It's got to have at least 2 levels, otherwise it's a constant. We've got predictor variables. A subset of predictor variables are independent variables. These might be a pre-existing characteristic used to classify the subjects, or it might be something that's under our control. And if it's under our control, we call it an independent variable. We've got outcome variables. A subset of outcome variables are dependent variables. These are the responses. This is what we measure. It's the dependent variable because we sure hope that it depends on the level of the predictor variable. That's all review, right? When we talk about measuring variables, we have either measured them categorically, which is our nominal or ordinal data. The levels are labels or words. They vary in quality or kind. You've been practicing this all term, right? This is very familiar to you now, right? Because it's going to be incredibly important starting now, because knowing whether you've measured your variables categorically or continuously is going to tell you exactly which statistics you are going to calculate. Yeah. Oh, that's true. So I said that we learned nominal, ordinal, interval ratio, and then I said we're dumbing that down into just categorical and continuous, and we will certainly just still stick with the categorical or continuous. But just as a reminder that it can be nominal, just naming data, or it can be ordinal, where it's got an inherent order. But those are different from continuous variables that are measured continuously, which are the interval and the ratio, and we're going to lump those together, the interval and the ratio. And those are values, they're numbers, they have a quantity or an amount, they go along a scale. You see me stretching out my fingers like this, which means scale, right? That you would say they're in days or in hours or in points. That's all review. So let's talk a little bit about the different types of statistics. First off, we start by describing the data we gathered. So we calculate descriptive statistics that summarize the observations that we gathered. So this is our way of just describing the actual data we gathered. We then calculate inferential statistics. And inferential statistics allow us to take that particular sample that we gathered and make an inference about the entire underlying population. So when we gather data, we gather it from one particular sample, but we're often really more interested in the underlying population. And those inferential statistics allow us to make inferences about that whole population. We will talk about how we choose the appropriate statistic. There's nothing creative here. It is a flow chart. It is if you have measured your variables categorically or continuously, so you just know how you look at the flow chart and you say, my predictor variable is either categorical or continuous, my outcome variable is either categorical or continuous, and that will tell you which statistic you're going to be calculating, which descriptive statistics and which inferential statistics. The other part of that flow chart is whether your population is normally distributed for this trait. What does that mean? Many characteristics are normally distributed in a population. So here's a continuum. If we've got a continuous variable, if I was to ask all of you to come down and stand in the front here and arrange yourself by height. Actually, no, you know what? I wouldn't want to mix the genders because then that wouldn't be normally distributed. So if I was just to say, all the guys, come down and arrange yourself by height, what we would find, and if you find someone who's exactly the same height as you, stand behind them, and then if we took an aerial photograph from up there, this would be the tops of the heads, right? And we would say that this characteristic is normally distributed. Most people are right around the average. Some people are very short, some people are very tall, but that most people are right around the average. What am I making with my laser pointer here? What do we call this shape? A bell curve, right. So that's what normally distributed means. And we assume, so a lot of characteristics are normally distributed in a population. This could be height, this could be IQ, that we assume that a lot of these characteristics are normally distributed, and then we will continue to talk about this because we then make assumptions and draw conclusions and make inferences based on this assumption. So that's the normal distribution. That's what we when we are choosing our appropriate statistic. It's partly based on whether you've measured your predictor variable and your outcome variable categorically or continuously. It's then, do we assume that it's normally distributed? They're not all, so when we look at a distribution curve like this, what we are saying is that everybody fits under this curve, that there's little aerial photographs of the tops of everyone's heads, and that the area under the curve is 1 or 100%. And we'll come back to those ideas next week. They're not all characteristics are normally distributed. Some characteristics are skewed. A skewed popular distribution has outliers at one end or at the other. So in this case, we've got, if this was normally distributed, it would look like this. Can you see that? And it doesn't. It's got these outliers. So the data is not symmetric around the mean. The tails are not symmetric. We describe a negative skew with the outliers or the tail being lower down on the scale, and a positive skew where the outlier or the tail is, the outliers or the tail is further up the scale. So once you've asked yourself those questions of how did I measure my outcome and predictor variable, and is this characteristic normally distributed, you will then just be able to use the chart that we will build in order to determine the appropriate statistics. So this is the chart that we're going to be building, where you've got, is your predictor variable categorical or continuous? You've got, is your outcome variable categorical or continuous? Is your, do you assume that this characteristic is normally distributed? And then we're going to come back to this over the next few weeks, and we're going to fill in what's the appropriate descriptive statistic for each of these rows, and what's the appropriate inferential statistic for each of these rows. Just a little word about notation. We're going to use letters like X or Y to represent the variables or the sets of the data. We use subscripts like X sub 1 and Y sub 1 to represent an individual score. So when we look at that data that we just gathered, let me pick on you for a second. Let's say you're participant number 1. And so you would have a participant ID number, and then you would have the your predictor variable, which was whether you were in the close proximity or the distant proximity. And so if we said that the predictor variable was variable X, and that was the proximity, your particular value for that is X sub 1. And then if you are participant 2, your value for that is X sub 2. And then in the next column over, we're going to have your decision. Did you say, definitely I would push that guy, or definitely I would not push that guy, or definitely I would save 5, or definitely I would not save 5? And that would be the Y column, that set, and you would each have a value there. Yes? They're to a particular individual score. So participant 1, if you wanted to say participant 1's outcome value, that would be Y sub 1. Okay? Yeah, no, you wouldn't. You're going to separate them into groups based on the predictor variable, the value of the predictor variable. We're going to use the letter N to indicate the number of observations. We capitalize it if it's the whole group. We use a lowercase if it's a subset of the data. We're going to use the Greek letter sigma to mean sum of. So if you see the Greek letter sigma, you're then going to be adding up whatever comes after that. So if we wanted to add up everybody's response to the outcome variable, we'd say sigma of y. Sigma y would mean add up those scores. Nothing new there, right? Okay. So let's talk about categorical outcome data. So if we've measured our outcome categorically, it's it differs in quality or kind. It's a yes, no. It's we're going to go back to the example of. Do you remember we talked about it last week of they did a survey in Psych 1 class, thinking of the last time that you had sexual intercourse. Did you wear a condom? Yes, no. So our outcome data was categorical. So let's talk about if we've only got one variable, we can just look at frequencies, and if we've got more than one variable, let's take a look at that. So this was that data that we looked at last week. So there were two pieces of data. Let's start with just the thinking of the last time you had sex. Were you sober? Yes, no. So we've just got a frequency here. We could graph that. We're just showing the frequency. With only one variable, there's not a whole lot of moving parts. There's not a whole lot we can do. We're just making a frequency claim. And so we're just saying, of this group, this many acted this way and this many acted a different way. It becomes more interesting when we have more than one variable. So let's complicate things a little bit. When we have more than one variable, we set up what we call a contingency table. So we lay out the levels of the two variables. Our predictor variable, were you sober, is measured categorically with 2 levels. Our outcome variable, did you use a condom, is measured categorically with 2 levels. And then we're going to count how many people fall into this group that said, yes, I'm sober, yes, I used a condom. How many people fall into this group? Yes, I'm sober, no, I didn't use a condom. And so here's the counts from that study. We call those the cells. They've got the counts in there. The next thing we do in this contingency table is sum our margins. So we add how many people overall were sober, how many people overall were not sober, how many used a condom overall, how many didn't use a condom overall. So those pieces of data are called the margins or the marginal values. We then add those up either straight down and straight across just to make sure that we get the same number. This is our sample size. I've used the capital letter N because this was the whole group. This was the entire sample. What can we do with that? Percentages. Percentages are going to make that so much nicer, aren't they? Because these actual observations are very dependent on the total sample size. So in order to compare 402 to 69, you need to say 402 of 471, 69 of 471. And if we were to run this study, let's say we ran this study again, but we surveyed 4,000 students. The raw numbers are going to be very different. But turning them all into percentages would allow us to very easily compare those. Let's take a minute and make sure that we all know what that would be. Let me just fill that in. All right. So let's start with the overall, the percentages of just one variable by itself. So what percentage of the group was sober the last time they had sex? How are you going to figure that out? So of the whole group, how many were sober, and what do you get? 85%. And then this, you're going to do 69 of 471. And what do you get? 15%. And that makes us happy that that adds up to 100 because that's the whole group, right? Of the whole group, 85% were sober, 15% were not sober. Of the whole group, how many used a condom? You're going to now take that number, that marginal value, and divide it by the total group. And what do you get? 81.5. And how many didn't use a condom? 18.5. And if you recall, this was for males who regularly use condoms, and so that looks like, yes, that was males who regularly use condoms. Let's drill down into the cells and also calculate percentages. What? I didn't... Oh. The projector turns off after 2 hours. So let's drill down into those cells and also calculate percentages. So we need to decide, well, if we have a clear predictor variable, then we're going to group the data by that predictor variable, and we'll say, so do we have a clear predictor variable in this case? Were you sober? Did you use a condom? Which is the predictor variable? Were you sober? So we're going to say, of the group that was sober, what percentage or what proportion used a condom? Of the group that was sober, what percentage didn't use a condom? Have you got those numbers? So, what's coming back on? There are 337 in the cell that was sober and used a condom. What are we going to divide that by? The total N? No, because we're not necessarily interested in saying of the whole group, what percentage was sober and used a condom. We want to say of the people who were sober, how many used a condom. So there were 402 that in all that were sober, and 337 of them used a condom. Have you got your calculations out? Or you've got the notes. So it's 84% of that group. Of the sober, 84% used a condom. And how many didn't? What percentage didn't? 16%. And then of the not so sober, what's the calculation here? It's 47 divided by 69. Of the group that was not sober, how many used a condom? What percentage used a condom? And didn't use a condom? So by summarizing it, by calculating proportions or percents, we have instantly made more sense of that data, haven't we? You can look at 84 and compare it to 68 and say, wow, those look really different. And you can look at 16% and compare it to 32 and say, those look really different. Whereas 65 of 402 versus 22 of 669 was not immediately obvious whether those were similar proportions or different proportions. So part of your job as a scientist is to analyze your data, to summarize your data in such a way that you can present it to your audience and they can see the differences that you are, the story that you're telling, the differences that are in that, or the similarities that are in that data. So by calculating those proportions or percentages, we could now very clearly communicate the differences there. So let's talk about how we would communicate that. First off, that's kind of the outline, the backbone of the contingency table. I wanted to make sure you had, the levels of the variables, the level of the other variables. These make the cells, and these are the margins. So how might we say that in text? Well, how might we write about these findings in text? We might say, in this survey, N equals 471, 81.5% reported having used a condom the last time they had sex. So I'm starting at that big level, just the levels of one variable. And then we're going to drill down into the cells. 84% of those who have been sober, lowercase n, and 68% of those who had not been sober, lowercase n, reported having used a condom the last time they had sex. So I'm giving the descriptive statistic, which is the percentage. That was our first descriptive statistic. Wasn't it easy? And I'm giving our sample size because you need to know, because we've turned it into a percentage, we've eliminated any information about the sample size. So we need to include that as well. We could present this as a graph. And so here's the title, the percent of sober and not sober, and I've got the ends who reported having used a condom the last time they had sex. So, actually, I think that just reporting the numbers in a narrative is probably the best way of reporting this information. I'm not sure that this graph really buys you anything. It's not. I think that it's just as easy to compare 84 to 68 as it is to look at that graph. We're going to save the graphs for the more complicated data where it really helps us to look at those graphs. Okay, so the comment is, in some ways, this looks like less of a difference than when we were looking at the numbers. Part of what we will talk about when we talk about graphing is making sure that you have your scale set appropriately so that you're not exaggerating any difference or minimizing any difference. But I think that's pretty accurate, but yes, I don't think it buys us much. So we've talked about categorical outcome data sets. There isn't much we do with them. If our predictor variable is categorical and our outcome variable is categorical, what is the descriptive statistic that we just calculated? Percent. And that's so there isn't a whole lot that we do with them. Things become much more interesting when we have continuous outcome. So when our outcome variable is measured continuously, first off, we can just do a group frequency distribution, but then we also can calculate measures of central tendency and measures of variability. Let's take a look at that. So first off, when we've got a continuous outcome data set, we can dumb it down and pretend it's categorical. So we can group it and make it categorical and then treat it like a categorical. Calculate that frequency distribution, draw a histogram. So you see this all the time, right? Where your score on an exam was continuous, but then it's been lumped into these somewhat meaningful groups of who was in the A range, who was in the B range, who was in the C range, and presented with that frequency, what percentage of the class was in each of those groups. And so we can take a continuous variable and sort of dumb it down into a categorical variable, or treat it like a categorical variable. But it's much more interesting to leave it as a continuous variable. So if we have continuous outcome data, we need to calculate two types of descriptive statistics. We need to calculate measures of central tendency, and then we'll talk about variability in a minute. Measures of central tendency are, well, what's the typical score? What's the score around which this group clusters? We've got three to choose from. We could calculate the mean. That's another word for average. We could calculate the median, which is the middle score. And we're going to go through all of these calculations. Or we could calculate the mode, the most common score. So I'm making the point here that you can calculate the median even if it's just ordinal data, and you can calculate the mode even if it's nominal or ordinal data. But for the most part, we're talking about continuous data, so we're talking about interval or ratio. So the mean, the notation we use is a capital M or an X bar. The formula for the average, you know this, right? You add up the scores, so that's sum of X, sum of the scores, divided by the sample size. So sum of the observed scores divided by the number of scores. So if this was our data set, if this was how you guys answered one of those questions, we would add those all up. We would count how many there were. We would divide that and say that the mean in this case is 5.67. The median is the middle score. We've abbreviated MDN or Q2. That refers to the second quartile. So if we lined up all of the data on a strip of paper and folded it in half, what is the score that's right there on the fold? What is the score that's right in the middle of all the data, where half of the scores are above that and half of the scores are below that? So you have to line the data up, you have to rank it. You then find the middle. So you could put them all on a piece of paper and fold them in half, but that might not be very feasible if you've got 300 observations. You could, knock the first one off and the last one off and the second one off and the second to last one off, but again, not very feasible when you've got 300 observations. It turns out that if you say sample size plus 1 divided by 2, that tells you which observation is in the middle. So you count up from the minimum score or down from the maximum score. Let me show you. So if these are our data points, oh look, they're already ordered. So that was the first step. Make sure they're in rank order. There are 15 of them. So I'm going to take 15 plus 1. That's 16 divided by 2. 8. I want the 8th score. 1, 2, 3, 4, 5, 6, 7, 8. This 7 right here is the observation right in the middle. What if I have an even sample? I've now got n plus 14 observations. 14 plus 1 divided by 2 is the 7.5 score. So I'm going to say 1, 2, 3, 4, 5, 6, 7.5. So it's somewhere right between these two. What do you think I do? So you're going to average those two scores. So it's somewhere right in between those two. You're going to average those two. The average of those two, sum them up, divide by 2, right? This is easy stuff, right? This part of the quarter, I think, I don't want to lull you into a false sense of security. Today should be pretty easy, okay? It's going to ramp up, don't worry. The mode is the most frequent. So what's the mode in this case? 9. It doesn't necessarily give us the best information. It's a very simple measure of central tendency. So some special cases. What if there are 2 or more modes? No problem. We deal with that all the time. We call it bimodal or multimodal. We're not worried about having more than one mode. What if there are extreme outliers? So we were talking just about if our data was normally distributed or if it was skewed. If there are outliers, the mean is very heavily influenced by those outliers. But the median isn't influenced much, at all about how far out something is. So let me show you that. If I put in a typo and type that as a 90 instead of a 9, so we've got this extreme outlier. The mean is now 11.06. Look at that data set. Does 11.06 seem like it's in the middle? It's being dragged out towards that outlier. The mean of when there wasn't that typo was 5.67. So the mean is very heavily influenced by outliers. So but the median is still that same number 7. Because it doesn't matter how far out that outlier is, it's still just one observation. It's just taking up one space on that piece of paper that you're folding in half. So if you have extreme outliers, which of these is going to be more accurate? The median, right, because the mean is going to be very influenced by those outliers. So, if our outcome variable is continuous, and we don't think that it's normally distributed, we think it's skewed, we think we have outliers, what measure of central tendency are we going to calculate? If we do think that our underlying data is normally distributed, what measure of central tendency are we going to calculate? All right, so those were measures of central tendency. That gives us the typical score, the number around which the data clusters. Now let's talk about measures of variability. So that's the spread. How spread out is the data? Is it really tightly clustered around the mean or the median? Or is it really spread out? How dispersed is it? And we've got three possible measures of variability: the range, the interquartile range, and the standard deviation. Let's start with the simple one. The range, the highest score minus the lowest score. What's the range here? 8. Couldn't be easier, right? Doesn't give you a whole lot of information. We won't come back to it very much, but it's giving you a very rough estimate of the dispersion. So it's a very simple measure of dispersion. When you have skewed data, when you have outliers, and you've calculated the median, you calculate the interquartile range to go with that. So the interquartile range, can you hear the word quarter in there? So you've taken all of your data, you've got it on a long strip of paper in your head, you've folded it in half to find the median. If you fold it in half again, you'll have the first quarter, the median, the second quarter, the third quarter, yeah? So you'll divide it into 4 equal groups. And you'll be asking, where's the boundaries of these quartiles or quarters? So it's like saying you're going to take you're going to find the median in the middle, and then you're going to find the middle of the bottom half, the median of that, and the middle of the top half, the median of that. Let's have a look. And so we always use median and interquartile range if we've got a skewed distribution. So here's our skewed distribution. First off, well, let me just show you. The mean is way up there, we said, and the median is down there. So we've 2, 4, 6, 8, 12, 14, 15. So there are 15 in our data set. The median, the second quartile, is that one right there in the middle. Then down here, which number is the quartile 1? So it's 3, but which 3 is it? This one here, right? So here are a quarter of the observations. Here are a quarter of the observations. How about up here? Where's quartile 3? Is that first 9? So you've divided it into equal quarters, and then you're looking, your question is, where do those land? So it lands as a 3 and a 7 and a 9. The interquartile range, we calculate not the range of the whole data, but the range of the middle half of the data. So between quarter 1 and quarter 3 is the middle half of the data. And we calculate what's the range of that. And so in this case, we would report that this has a median of 7 and an interquartile range of 6. And that tells us, that gives us information about how spread out it is, where's the central tendency, and how spread out it is it? How dispersed is it? We would display this in a box plot. When you're creating a box plot, so you need to set your scale, and note that it's not the same as your data here, because we've got that 90. We got to have the scale up there. You put your median in. You then draw a box around the middle half of your data. So that's quartile 1, quartile 2, quartile 3. You then draw whiskers out to the minimum score and the maximum score. And this is called a box plot or a box and whisker plot. One of the things that you're looking at when you look at this, the data presented this way, is at how symmetrical this is, or how asymmetrical this is. And it's a little bit counterintuitive, where something that's really big, like this whisker is really big, it seems like it's sort of big and long and important, but it actually means that there are very few, that the data is really spread out. Because remember, these are equal quarters. So a quarter of our data is crammed together right here. Another quarter of our data is crammed together right here. Another quarter of our data is really, really concentrated. Isn't that kind of counterintuitive, where it's like the smaller it is, that's just, it's telling you that it's really concentrated. And then a quarter of the data is spread way out, all the way up there. So you need to not be taken in by the larger size of the whisker, and think about it in an opposite way, and be thinking about that's really tightly clustered, that's really concentrated. When do we calculate the interquartile range? What does that go with? That goes with the median. So if our outcome variable is continuous, but we have outliers, it's skewed, we'll be calculating the median and the interquartile range. If our outcome is normally distributed, we've calculated the mean, and when we calculate the mean, we calculate the standard deviation to go along with that. So this, again, is a measure of variability. It's a measure of how closely those scores are clustered around the mean. The word standard deviation literally means the standard or the average amount that the scores deviate or differ from the mean. So these four distributions all have the same mean, right? The mean, the central tendency is right there in the middle. But this one is really tightly clustered. It has a very small standard deviation. And this one is really dispersed. It's really spread out. It has a very large standard deviation. So if we take scores on a quiz and we calculate the mean, we want to know the average amount that those scores differ from the mean. What are we going to do to start with? How would we know how much, if the mean is 5, how much does this one differ? So if the mean is 5 and a score of 4 differs by 1 point, how did you do that? So the difference is subtracting, right? Right? That's all it is. So you're going to subtract, you're going to find out how far away each of those are from the mean. And then you're going to average those distances. You're literally just going to add up those little pink lines and average them. That is all that the standard deviation really is. Okay, it's a little bit different. So, how do we calculate it? So here are the scores. The mean is 5. We're going to start by subtracting the mean from all of those scores. So we've got the score minus x bar, or the mean. What would happen if we added those up right now? I hope we'd get 0. We should get 0 because that's what the mean is. The average is right in the middle. There should be just as many far away above as there are far away below. So we got to get rid of those negatives. I bet you can think of 2 ways of getting rid of the negatives. Absolute value. Our life would be so much easier if those darn statisticians had chosen that. But those darn statisticians decided instead that they would square it. So they then say, take each score minus the mean and square it. Okay? There we go. We've got each score minus the mean squared. Now we can add those up. So I've got the Greek letter sigma there. The sum of that is 58. We call this number the sum of squares. We're going to come back. You're going to hear that in a couple of different places. And you're just going to remember that has to do with the standard deviation. That has to do with how tightly those scores are clustered around the mean. So the sum of squares is the sum of each score minus the mean squared. The next step, we're going to have to average them, right? How do we average that? Divide by the sample size. We're actually going to divide by n minus 1 because we are being very modest. We're not overstating it. If we have a very small sample size, we want to overestimate how spread out that is. So we're going to say, we're going to divide it not just by n, but by n minus 1. If we have a really large sample size, dividing something by 100 versus dividing by 99, there's almost no difference whatsoever. But a very small sample size, dividing something by 7 or by 6, there really is quite a big difference. Yeah. So 7 was 1, there are 1, 2, 3, 4, 5, 6, 7. So n is 7. The sample size in this case is 7. We've ended up with 9.67. Is that our standard deviation? Is that the average of those distances from the mean? No. What else do we need to do? We need to take the square root because we squared it, so we have to unsquare it. So we'll take the square root of that, and we get this number 3.11. And for this sample, it has a mean of 5 and a standard deviation of 3.11. I am going to ask you to calculate averages and standard deviations on the homework and on midterm 3. Because it's not that hard. I think a lot of people just see standard deviation and kind of panic. And you guys are going to own it. All right? Take a deep breath. Are you ready? Take a deep breath. Okay? It's okay. This is what we just did. So the standard deviation equals the square root of each score minus the mean squared, summed up, divided by n minus 1. Okay? So it's those average distances from the mean. There are other calculation formulas that are functioning the same. I'm going to ask you to use this formula. I think your book uses one with just n, but I'm going to ask you to use this formula. Where does standard deviation go on our chart? Where does it go? Oh, it goes with the mean, right? If we've got a categorical predictor variable, continuous outcome variable, we think it's normally distributed, we're going to describe that data with the mean and the standard deviation. Let's do a couple of clicker questions and make sure that we're remembering or we're understanding that. Oh, it's on numeric. I'm sorry. That's all right. I'll change it. Okay. Go. Absolutely. That's right. You guys are great. 93% of you are recognizing that you can only calculate a mean if your outcome variable was measured continuously, if it was values, if it was scores. You can't say the average of yes, no, but you can say the average of on this test or the average of this score. All right, and you're not quite as certain about this, but you're calculating percentages if your outcome was measured categorically. So if your outcome was categorical, we calculated percentages. If your outcome was continuous, we're mostly going to focus on this row of the mean and the standard deviation. There are 3 measures of central tendency, and there were 3 measures of variability. The 3 measures of central tendency all start with the same letter. Isn't that convenient? Okay, you guys can recognize M's. So the mean, the median, and the mode are all estimates of central tendency. Standard deviation is a measure of variability, of how spread out the data is. All right, well done. What goes with the mean? The standard deviation goes with the mean. So, the only one we haven't talked about is when we've got continuous outcome data and continuous predictor variable. So, with a categorical predictor variable, that makes groups, right? The group that saw this information or the group that saw that information. And so it makes sense to calculate group averages. But if our predictor variable was continuous and our outcome variable was continuous, we don't have groups. We can't calculate group averages. We have talked about this before. Do you remember? How do we display continuous and continuous predictor and outcome? In a scatter plot. And that turns out really is kind of the way we would describe that data. So we don't, there's no way to summarize it by just calculating the average and the standard deviation. We show all members of that data set as that scatter plot. So far today we have said when you are asking what your descriptive statistic is, you've got to ask how did you measure your outcome variable? If it was categorical, you're going to be calculating percentages and contingency tables. If it was continuous, normally distributed, mean and standard deviation, skewed, median and interquartile range. Always include your sample sizes, your n's. All right, I will see you next week.